Okay, we're going to take a look at another problem. So this time we're going to look at this problem here to do with concentric circles. So we've got two concentric circles. Express the area of the shaded region in terms of x, and then we have this very complicated looking thing. So let's have a bash. So we'll start off, this is question 3c. We'll start off as in all these things by drawing it. Try and fill in some useful triangles if we can. So that's BC there. The length BC is 2x, so we know that this whole, we're drawing a line there. Drawing a line there. So we know that this is x and this is x. So BC is 2x, so you can draw a line down that's perpendicular, because where the tangent hits it is perpendicular. These are both big radiuses, so both those triangles are the same. Whereas to express the area of the shaded region, now the shaded region is this donut here. So we want to write the area of the shaded region in terms of x, which looks a little bit tricky. So we better start by, well, the only way we can find the area of the shaded region is as the area of the big circle, take away the area of the little circle. So we better give the big circle a radius and the little circle a radius. So let's call the big circle's radius, let's call it capital R, because it's big. So let's call the radius the little circle, which is actually this line here. So let's call that radius little r. So we have the area of the big circle is pi big R squared. The area of the little circle is pi by little r squared. So the shaded area is pi by big R squared minus pi by little r squared. And we can factor out a pi, that's r squared, big R squared minus little r squared. Now looking at what we have up here, this is where you need to be a little bit kind of ingenious and spot that, as we said, this is the right angle triangle here. So because it's a right angle triangle, we can use Pythagoras' theorem. So let's just draw out that triangle again. So this is x, this is little r, and this is big R. So Pythagoras' theorem says that big R squared is little r squared plus x squared. Now if you look at what we have for the shaded area, this is what we have up here. We don't want this bit. We don't want the bit with the r's. Pi is fine because pi is a number. We don't want this bit here. So if we have a look down here, can we manufacture big R squared minus little r squared down here? And we can. We just minus r squared from both sides, or bring that little r squared across, whatever way you want to think about it. Whatever way you think about it, big R squared minus little r squared is just x squared. So the shaded area, this works out very nicely, is pi by x squared. That's kind of surprising. It comes from, when you look at a question, first of all, draw the picture, fill in any extra triangles that are going to help if you're doing trigonometry. If you're asked something about an area, go in and find the area, and there isn't any other way to get that shaded area except as the area, the big one, take away the area, the little one. So that's what we do, and then you look and you say, well, what do I want to eliminate, and is there any way I could write that in terms of x? Okay, so that's when you hopefully spot Pythagoras' theorem. Alright, so that's the first bit. It certainly helps if you get that bit first. Right, the second bit of the question. Second bit of the question asks us to show that in the case where the radius of the outer circle is 2x, show that the portion of the shaded region that lies below BC has that area. Alright, okay. So part 2 says the radius of the outer circle, that's big R, is 2x. Well, that means that we can figure out what the little radius is in terms of x. So Pythagoras' theorem says 2x squared equals r squared plus x squared. When you square 2x, you get 2x by 2x, that's 4x squared, is r squared plus x squared. If you bring the x squared across, or minus x squared from both sides, you get 3x squared equals r squared. And if you take square roots, you get the square root of 3x squared, which is root 3 by x, is equal to r. So we have an expression for what the radius is, the little radius. Okay. So now what we need to do is we need to try and find what the shaded region below BC is. Okay. So let's draw a slightly bigger diagram. Okay. So this is x, and this is 2x. We know this is a right angle. We would like to find this angle A here. Now the reason we'd like to find that angle A is that what we're going to do, and once you've done a few of these, you'll hopefully recognize that if you're trying to get the area of a shape that looks like this, which is exactly what we're trying to do here, we're trying to get the area below the line BC. So if you're trying to get the area of a shape that looks like that, the way you do it is you get the area of this sector using the formula in the log tables, which we'll talk about in a second, and you minus the area of this triangle. Now if you go to the log tables, you can find that the area of a sector, it's out near the front, the area of a sector is pi r squared theta over 360 if it's in degrees. It's slightly different if it's in radians. So that's the area of the sector for when the angle in there, that angle there is theta, and the area of a triangle is half AB sine C. So again, if we know that angle there, once we have that that's x, once we know that angle, we can find the area of the triangle. Once we know that angle, we can find the area of the sector, and the sector take away the triangle is that little bit down there, which is the bit that we're looking for in this question. So that's why we're going looking for that angle. Now because the whole thing is symmetrical, we might as well use the right angle triangle, and then we can just double the angle to get the whole angle. Okay, so let's get this whole angle, we drop a perpendicular, we find that angle, and then we double it to get the full thing. Okay, so over here, this is where slope gets over, because we're in a right angle triangle. If you're in a right angle triangle and you just care about sides, use Pythagoras theorem. If you also care about angles, use slope gets over. Alright, so this side is the hypotenuse, this side is the opposite. So we're over here, so sine of A is opposite over hypotenuse, which is x, over 2x, which is 1/2. And if you look up the log tables or get a calculator, you can find that A is equal to 60 degrees, 30 degrees, 30 degrees. You just check that by getting the inverse sine of 1/2. Sorry, see that? 30 degrees there. So the inverse sine of 1/2 is 30 degrees. So A is 30 degrees. So that whole angle there is 60 degrees. So what we have now is 60 degrees, and this is 2x and 2x. So we're going to get the whole area of the sector, and then we're going to minus the area of this triangle. Okay, so let's do that. So the area of this sector here, said that the area of the sector is pi r squared theta over 360. We're going to be taking away half AB sine C. So that's pi by 2x to be squared by 60 over 360 minus half one side, so 2x by 2x by sine of 60. Okay, So fill this in, that's 4x squared, so that's pi by 4x squared by 1/6 minus, so we're left with 2x times sine of 60, and you can look it up in the log tables. Will this calculator give it to me? No. Right, so this calculator, being an old one, just gives me the decimal expansion. So that's √3/2. It's in the log table. And that should be an x squared. So that and that cancel. Over here, it goes in 3 times, that goes in twice. So we're left with 2 pi x squared over 3 minus x squared by the square root of 3. Whoops. Now let's just finally take a look at what we're trying to prove and see, is this anything like what we're looking for? We're looking for an x squared factored out, so let's factor out an x squared. We get 2 pi √3 when we factor x squared out from here, and when we factor x squared out from here we get minus √3, and that's exactly what we're looking for. Okay, so with these, when we were given the extra information, hopefully we got the first bit of the question. When we're given the extra information for the second bit of the question, you fill it in, we get rid of that little radius that we had, and then this will kind of come up again and again. If you were looking for an area like this, the handiest way to get it is as the area of a sector, take away the area of the triangle. Okay, and because these are both radiuses here, here and here, then finding this angle allows you to find the area of that triangle using half a by b by sine the angle in the middle. And over here, it's pi r squared by theta over 360 if t is in the middle. Okay, so that's pretty much, that's it.